Sir, with a short intro about you, will start the session, sir. Later, people will join with us, sir.
Okay, sir. Okay, okay, okay.
It's my privilege to welcome you all to the day six of ACT Atal sponsored online faculty development program on engineering trends in advanced materials, smart manufacturing techniques, and Asian metrology. Today, we are honored to have with us Dr. Manmohan, an accomplished material scientist and a postdoctoral research fellow at AJOU University of South Korea. Dr. Morgan serves as an 8 years of experience in material synthesis, characterization, and thermal engineering storage, thermal energy and storage system. His expertise span across the solar thermal storage, photothermal conversion, multifunctional energy storage, and the development of nano-energy PCM composites. His significant contribution includes 20 SCI index journal publications, several Scopus articles for Indian design patterns and book chapters. He is also an actively engaged in international research projects, include prestigious National Research Fellowship, South Korea, focused on the advanced multi-component PCM for solar thermal storage. With a strong background in advanced characterization techniques such as DCS, TIC, and SEM, XRDS, and XPS, on his passion of applied research in energy storage, Dr. Manmohan continues to bridge gap between the cutting-edge research and industrial application. We are delighted to welcome you, sir, for this session.
Thank you, sir. Thank you so much. So, first of all, am I audible, sir?
Yes, sir, your audience.
Okay, okay. Okay, sir. So, I would like to thank convener of this FDP, Dr. E. Siva Kumar, and co-convener Mr. M. Vinod Kumar for organizing such interesting FDP on emerging trend in advanced material, smart fabrication techniques, and precision metrology. So, and also I would like to thank the organizing committee of this Atal FDP for their seamless coordination and continuous effort. So, first of all, I would like to share my PPT. Just a minute. Sir, is it full screen?
Yes, sir, your screen is visible, sir.
Okay, so entire screen is visible, right?
Yes, sir.
Okay. So I would like to introduce my topic is a small part of my research work what I am doing here. That is a multifunctional phase change material for energy storage and thermal management. So I am from the Department of Material Science from the AJOU University, South Korea. So I would like to start my presentation with the world energy scenario, and I will try to correlate this energy scenario with the phase change material and our childhood memory. So you can see in the slide, like there is a continuous increasing demand of energy from I have plotted this from 1965 to 2025 2050. So there is continuous increase, and also after certain time period like after 2005 or 2006 there is a gap between demand and supply. So this increasing gap between demand and supply of energy requires the continuous development of sustainable clean energy sources. So as you know, there are a lot of clean energy sources like wind energy, solar energy, geothermal energy. And among these all energy sources, solar energy has been considered as a promising energy carrier for the future because it is abundant in nature, and also less effort is needed as compared to other renewable energy sources to get it from the our nature. So as we know, solar energy is available in the daytime only. So we can correlate the solar energy like our childhood memory when we are getting money from someone and we are storing that money in earthen pot to collect the to collect the money for particular some purpose or some specific purpose. Similarly, phase change material, like my topic is basically deal with the phase change material. Phase change material also work in the similar principle. When we have abundant energy, solar energy in the daytime, we can store that energy in the phase change material as a thermal energy. And when we need, basically when we need daytime also and nighttime also, but in the night time solar energy availability is not available, so in nighttime we can utilize that stored energy in the phase change material. So this is the first introduction of the phase change material. So we can conclude this like phase change material is a material that stores thermal energy in the daytime, and we can utilize that energy while the solar energy is not available basically in the night time. So in the next slide we can see world energy scenario and the phase change material. So I would like to correlate phase change material with the losses of energy. So when the loss of energy occurs, see, as we know, energy can be categorized in two type: low grade energy and high grade energy. So low grade energy is what that is we are directly utilizing that energy in our daily life or day by day life. That is a low grade energy. High grade energy refers to a form of energy that can be easily converted into the work with minimum losses, such as electrical, mechanical, and chemical energy. Whereas low grade energy, in contrast, more dispersed and less efficient for the performing useful work, such as low temperature thermal energy or waste energy. Now, that the importance comes when we convert high grade energy to low grade energy. First of all, I will start from the solar energy. When solar energy is get converted into the high grade energy, that is the electrical energy. I'm considering electrical energy as an example of high grade energy. So when the solar energy is get converted through PV panel, photovoltaic panel, that have very less efficiency, around 15 to 22%. So significant, we can say significant amount of energy is going in the losses. So we are getting only 15 to 20%, 22% efficiency for conversion of solar energy into the electrical energy. Now further moving this high grade energy, that is electrical energy, to the low grade energy for our daily application, that is in the, I'm considering here heat as a low grade energy for our daily life, because basically I will deal with the heat. So I'm considering heat as a low grade energy. So now conversion from high grade to low grade energy, the efficiency is 80 to 95%. That means converting electricity to the heat, there is a efficiency is 80 to 95% because of the joule losses. So here also we are getting loss around 15 to 20%. So this loss, why this loss is occurring? Because we are converting and we are utilizing high grade energy to the low grade energy. So our energy flow start from the high grade and it finish with the low grade. So conversion from high grade to low grade consist of losses. But what PCM does, PCM here the PCM comes with the no loss or very minimum loss, because what PCM does, it stores heat in the form it stores energy in the form of heat and delivers in the form of heat. And heat, I am considering heat as a low grade energy. So basically PCM stores low grade energy and delivers low grade energy. So there is no conversion between the grade of energy. It means low grade to low grade is taking place, and there is a very less loss, or we can say there is no loss. So this is the advantage of phase change material. Now I would like to introduce phase change material. So first of all, I will introduce phase change material with the ice and water because it is a very fundamental material that we are looking from our childhood. Ice and water. Ice and water is a first phase change material that exists in three phases: ice, water, and vapor. So based on temperature and pressure, the same material exists in three different phases. So I can consider it as a phase change material because it interacts with the heat and convert it phase change. So whenever material interacts with the heat and convert or change its phase, I will consider as a phase change material. So first example was ice and water. Similarly, paraffin wax is the most common research and even industrial applicable phase change material, paraffin wax, or simply we know it as a wax generally used in our daily life to make a candle. So that is a phase change material, paraffin wax. It is a organic phase change material. And third category is salt hydrate. That is also a phase change material. In next slide, we will discuss about the salt hydrate. What is the property? So salt hydrate is also phase change material. Among these three, what I am showing in this slide is we can differentiate among these three through the melting temperature or melting point. So the lowest melting point or lowest phase change point of the three phase change material is ice and water. After that, paraffin wax comes in the picture. Slight more phase change temperature as compared to the ice water. And third one is the salt hydrate. That is the in this among these three highest phase change. And uh, next, you can see in this slide also the four different stages through which the phase change takes place and the heat interaction takes place. In the first phase, you can see the phase change material in the top is in this center picture. You can see in the top the phase change material. First phase is in the solid phase. When the temperature rise through the heat, it starts melting and the crystal becomes liquid. The rise of temperature takes place. Similarly, when the temperature rise takes place, the heat energy is absorbed by the PCM when it start melting. Further, in the third stage, the melting become complete and the solid will become total liquid. It starts storing the heat. Further, in the next slide we will discuss about how it will store the heat and type of the storage mechanism, how the phase change material will store heat and type of uh, heat like sensible heat and latent heat. So after that, when the phase change material completely melt in the liquid phase, now the temperature will fall down and temperature drop. That time again the material will start to solidify. When it starts solidification, the heat energy is released by the PCM and it will get solidified. So through this fundamental mechanism between solid to liquid and again liquid to solid transition, the heat interaction takes place, and this interaction of heat further we can utilize to develop a thermal energy storage system, or we can develop a thermal energy storage material. Now types of PCM. So this slide you can see the types of PCM. Basically, two types of PCM has been researched: organic and inorganic. Nowadays, when the sustainability comes to the picture, bio-based PCM also getting involved in the research. So in the first type, organic PCM, which is the carbon based material often derived from the natural and synthetic sources. Whereas in organic PCM, in the second type, you can see these type of materials are salt based material with higher thermal conductivity. Now I would point out the thermal conductivity, which is the fundamental property of the phase change material, for which the research is getting involved day by day, involved to increase the thermal conductivity, or I can say thermophysical property. So, in continuation of type of PCM, paraffin wax, which is derived from the petroleum, that is N-octadiene and N-icosane. The advantage of this organic PCM is a stable nature during the thermal cycle, non-corrosive in nature, predict, predictable melting points, wide availability. Whereas in case of inorganic PCM, salt hydrates composed of salt and water. The advantage of this inorganic PCM is a high latent heat, non-flammability, and cost effectiveness. Whereas disadvantage of organic PCM is its low thermal conductivity. This is the major point for which the continuous research is going to increase the thermal conductivity of the organic PCM, because the organic PCM is always having the lowest thermal conductivity among other PCM, and also the flammability. At certain temperature, the organic PCM takes place fire, so that is the disadvantage. Whereas in case of inorganic PCM, the disadvantage is phase segregation, supercooling, and corrosion. So corrosion, I would like to point out corrosion as a disadvantage for organic PCM, because if we are going to develop certain thermal energy storage system, in that case we have to store the phase change material in a container, metallic container, I can say metallic container. That container, we wish to continue the system at least 5 year or 10 years. But in that case, when we are utilizing inorganic PCM to store the heat in that container, so the disadvantage is that inorganic PCM corrode the container. So that is the major disadvantage of inorganic PCM. So whereas in case of organic PCM, the disadvantage is its high cost and limited availability. Not for all, but certain type of inorganic PCM is having little scarcity for this for their availability. Now, bio-based PCM also derive from the renewable natural sources like soy wax, palm oil, even coconut oil also considered as a bio-based PCM. So their advantages are eco-friendly, biodegradable, non-toxic, and disadvantage are limited thermal stability and higher cost. So certain like I would like to say, like some terms, thermal stability and thermal conductivity. These terms further we are going to discuss in our upcoming slides. So don't worry about that. These terms we'll discuss in detail also. So now in the fourth picture you can see the plot among the melting enthalpy and melting temperature. So that plot is a combined plot for the all three types of PCM. That is the plot for their melting enthalpy and melting temperature. So now the term comes in the picture. What is the melting enthalpy? So melting enthalpy is defined when the phase change material converts its phase. So in that case, how much amount of heat that needs to change its phase from solid to liquid. When it is changing its phase solid to liquid, that means we need to supply the heat, or we need to give heat as an input. Whereas when it solidifies from liquid to solid, that much amount, the similar amount of heat it liberates or it release from the material. So melting enthalpy, similarly melting temperature. So these two parameters, melting enthalpy and melting temperature, we have to focus while we are designing application for thermal energy storage, because these two terms defines the material thermophysical property. How much amount of heat the material can be stored while designing such system. So as you can see, the salt hydrates is having the highest melting enthalpy. That means same, if we are considering 1 kg of phase change material, the salt hydrates can store the highest amount of heat inside it. Whereas the ionic liquid, that is also a phase change material, it stores the same amount, 1 kg will store less amount of heat. So through this plot we can understand the property of material for particular application, how much amount of heat that can be stored. Now, fundamental principle how the phase change material deals to store the heat when we are using as a latent heat thermal energy storage. So now I would like to introduce the thing latent heat and sensible heat. Before understanding the principle of phase change material, we should know the sensible heat and liquid heat. So first, sensible heat. What is sensible heat? When the temperature changes and the material remains in its same phase, there is no phase change, and temperature is continuously rising, that is considered as a sensible heat. Whereas when the temperature become constant and the phase of material, like from solid to liquid or liquid to solid, the material is changing its phase, that is considered as a latent heat. So the thermal energy storage system works on two kind of heat, the sensible heat also and latent heat also. So this presentation is basically meant for the latent heat thermal energy storage when the material is changing its phase rather than the sensible heating. So you can see in the picture, first material will start in from its solid phase. You can see in the picture A, figure A, when the material is in solid phase, blue color you can see in the solid phase. When we are giving heat, for example, from the solar heat, solar energy, the material is getting heated. First, what will happen? The temperature will rise. At that time, the temperature will rise, but the phase will remain same. You can understand this thing with household water heating also. When we start water heating, that time, so for example, say 25 degree, the initial temperature of water. When we start boiling of when we start heating of water, the temperature will rise, but there is no changes in the phase till 100 degree. Once the temperature will reach 100 degree, the phase change will occur, then the liquid will become vapor. So similarly, here also the material, phase change material, will initially solid and temperature will rise till what temperature? Till its melting temperature. After that, once the temperature will reach to its melting temperature, the material will become constant temperature. After that, even we are supplying the heat, temperature will not rise significantly, or we can say constant temperature. That time, if we are continuous heating, the material will start absorbing heat inside itself, and that phase change will start. That means solid will become start liquid. After a certain time period, the liquid, the all material, whatever the mass of material, it will completely liquidify. Then again, if we are continuously heating, then the temperature will rise again, and the in that case also the material will remain at same phase, that is the liquid phase, but that time also the temperature will rise. So here you can see three phases. First is solid to solid, then second phase is solid to liquid, and third is the liquid to liquid. So the latent heat thermal energy storage, that is the widely research field in the phase change material, that is the latent heat thermal energy storage material. In that case, the second intermediate phase, that is the solid to liquid or liquid to solid, that phase only, heat interaction in that phase only is getting utilized in latent heat thermal energy storage. So this is the principle of phase change material. And also I would like to say, like, if anyone having doubt in between this my slide, they can ask question so that I can answer more better way, rather than the last if they will ask. So anyone having doubt, they can ask in between also. Now, after this introduction of phase change material, the limitation of phase change material, this limitation, I can say this limitation become the research area for the phase change material. Basically, all kind of phase change material is suffering from the low thermal conductivity. You can see most of the PCM, whether it is organic or bio-based, from organic to bio-based, even inorganic and eutectic also, they have thermal conductivity in the range of 0.15 to 0.40. That is very low thermal conductivity. If you will compare with the thermal conductivity of the copper, maybe we can say it is 1,000 times lower than the copper thermal conductivity. So all kind of these phase change material, they are always suffering from the low thermal conductivity. So major focus as a material science background research, not from the mechanical, I can say, the inherent thermophysical property that deals with the thermal conductivity also. Among apart from that, other thermophysical properties are also there, like latent heat. We will discuss this thing in next slide also. So thermal conductivity is a major challenge to for phase change material to integrate for latent heat energy storage material, or we can say thermal energy storage. Apart from that, other limitations are also there for phase change material, like supercooling, phase separation, volumetric expansion, cost corrosion, and environment safety, thermal stability. These kind of limitation are also there. In case of volumetric expansion, we can understand, like when the material is in solid phase, having less volume as compared to the liquid phase. So if we are designing a certain system that stores phase change material to capture the thermal energy, to store the thermal energy, we have to consider its volumetric expansion. When it will solid and it will convert its phase to the liquid, that time the volumetric expansion will be there, and in that case, uh, we have to consider the uh, container volume also. So this is the limitation. Also, certain phase change material that having specific thermophysical property need to develop a system that having a might more cost as compared to the other phase change material that having the limited thermophysical property. So this is another problem with the phase change material. Thermal stability is also one major challenge with the phase change material. Like if we are using phase change material at certain temperature, say for example 80-degree, our system is designed for 80-degree. In that case, if the we have to understand what is the maximum temperature, after that the material will start its mass decomposition. That means mass is converted to the vapor. So that is we have thermal stability. That means we have to understand till what temperature we can utilize certain phase change material. So these are some disadvantage, or I can say limitation of the phase change material. So basically, in this today's presentation, I will discuss with thermal conductivity. Now, the required properties of the phase change material. What are the properties that requires from for the phase change material? That is a thermal property, physical property, chemical, as well as economical or practical consideration. So thermal property deals with the high latent heat of fusion. That means we need whatever properties here mentioned is required from the phase change material to develop a system. So high latent heat of fusion, that ensures the significant amount of energy to be stored or released during the phase change. If the material is having high latent heat, that means it can store more amount of heat. And then appropriate phase transition temperature, it should match with our input temperature. Say for example, we are utilizing phase change material to store solar energy. That means it, if we are connecting phase change material with solar energy through concentratic concentration solar collector, in that case the temperature range will be around based on the design, say for example 80 or 120-degree. So that time the phase change material, phase change temperature of material should match with the input temperature, where from where we are getting the input of heat. Then high thermal conductivity, definitely it needs for quick heat transfer during charging or discharging. Charging means melting of the phase change material or storing heat, or discharging means solidification, when it will release the heat for utilization during the night time. So thermal conductivity. Similarly, thermal stability is needed for consistent performance over repeating period of cycles. When, because if we are developing a system, it's not for a single time investment. We want to utilize a system frequently, or continuously. That time thermal stability should be ensured that it should uh, maintain the performance, similar performance for repeated cycle. So these are the thermal properties. Similarly, physical properties also a small volume change. The expansion of the phase change material while phase and during its phase transition should be minimum to avoid the mechanical stresses or leakage in the system. Wide operating temperature range, that should ensure for function reliability across application specific temperature. Low vapor pressure, when the material is changing phase from solid to liquid, it should not create significant high vapor pressure so that leakage can occur in the system pipelines. So this is the physical property of the phase change material. Similarly, chemical properties, non toxicity, chemical stability, compatibility with the container material that we already discussed in the terms of corrosion. So these are the chemical properties that we needed from the phase change material. As well as in economical or practical consideration, we can say cost effectiveness. Definitely, it is very important. Ease of encapsulation. The phase change material should be easily accommodate or encapsulate in the container so that we can design system effectively. Recyclability, that means uh, for certain time, after certain time period, if we are uh, observing that degradation in thermophysical property, say for example 2 years or 1 years, uh, after certain time period the material will not perform as the first commissioning. Then in that case, if we want to recycle the material or we want to dispose that material, that also should be considered recyclability of the material. So these are some fundamental properties we needed from the phase change material. Now we can see the thermal energy storage material can, how it can be classified. So before starting the classification of the phase change material or thermal energy storage material, one thing please consider, when sometime I can say phase change material or sometime I can say thermal energy storage material, because thermal energy storage material is a vast category. In that, different material will comes, not only the phase change material. And phase change material is a one category of the thermal energy storage material. So don't be confused in terms of thermal energy or PCM, both are same. So PCM is a uh, part of thermal energy storage material. As you can see in this picture also, there are lot of there are four types of thermal energy storage material. In that, one case is a phase change material. So before this classification, you can see in the left side picture, very old picture, you can see during the ancient time. Now you can understand what is the phase change material for practical application. Before we discuss in the terms of material science what is the phase change material, but now you can see as a mechanical background or as a thermal background, what is the practical application. This picture shows um, the use of pebbles or concrete rocks. What they does during the ancient time, they store the rocks in the one bed, that a metallic bed. Below that they start the fire through wood or through charcoal, whatever the things. The wood or charcoal burns and it get heated the pebbles or rocks. After that certain time period, the rocks will get heated. Through the convection, the heat of the rocks will pass through the passage and it will go to the house. So in that case, what we can say, the pebbles will store heat, whether, but in that case they are not converting its phase. That is the ancient time when the energy storage is taking place in the rocks as a sensible heat storage rather than the latent heat storage. Here the rocks are not taking place any phase change, but they are storing heat for a particular time period. After that, when in the night time, or also we can say when the fire is get off, That time also the rocks will release continuously release the heat, and it will go through the passage to the inside building. So this is the application of the energy storage material. Now come to the picture that thermal energy storage can be classified in sensible heat storage, latent heat, thermochemical, as well as sorption heat storage. The sensible heat, as I already given the example, rocks, water, soil, thermal oil, molten salt. These kind of materials comes under the picture of sensible heat energy storage material without any phase change. That means the material whatever comes in the picture of sensible heat, it will remain in the same phase but store heat. Whereas in the second case, the latent heat energy storage, it is solid gas PCM, liquid gas PCM, solid to solid PCM, and solid liquid PCM. In that case, the material will change its phase, maybe solid to liquid, liquid to solid. And further, if we want to classify this solid to liquid PCM, basically for today's presentation, I'm dealing with solid to liquid PCM or liquid to solid. That means latent heat thermal energy storage, when the material is changing changes its phase from solid to liquid. Further, it can be classified in organic, eutectic, and inorganic. In case of organic, the material like polymeric organics, inorganics. Similarly, eutectic means eutectic, I can say combination of two different material like inorganic, inorganic, organic, inorganic, or organic, organic. So this type of material, if you will combine two different phase change material, that comes under the picture of eutectic solid liquid PCM. In next category, you can say inorganic like salt hydrate, hydrochlorides, carbonates, chlorides, nitrates. This comes in the example of inorganic solid liquid PCM. Inorganic solid liquid PCM, that comes in the broad category of latent heat thermal energy storage. Further, the third category is a thermochemical, where the thermochemical reactions are taking place to release the heat, or through the through input of heat, the thermochemical reactions are taking place. Like I can say metal hydrides, when the hydrogen is absorbing in the certain metal powder, the chemical reaction takes place and the heat is getting released. That is also a kind of energy storage through thermochemical energy. It comes under the picture of thermochemical energy storage. Similarly, sorption heat storage, that that can be further classified as a physical absorption and physical absorption. That is a more deeper chemical reactions where the sorbent absorbs certain material and it release heat. So that is a sorption and a heat storage. That is not a discussion of this presentation. Now, PCM as a thermal energy storage material. So this picture shows some example or application of phase change material, how phase change material can be utilized for certain application. So through this picture, you can see phase change material has been filled in certain region or certain volume of the house or certain container. I will start with the example figure A. In figure A, you can see the TES material in the bottom. You can see in the schematic of the Rankine cycle, you can see the TES material has been filled in the container. The it stores heat from the parabolic through collector, and the material stores heat. Further, there is a heat transfer fluid that takes heat from the TS material, and the vapor heat through the heat exchanger. The vapor is formed and it starts the turbine, or it drives the turbine. But this now the question can arise, why the TS is implemented in this system. As I already told that TS is implemented to store the heat during the availability of the solar energy, to run the continuous cycle of this Rankine cycle, or for example whatever the cycle to generate the electricity. It is not possible to always getting thermal energy from the solar energy. So to store the heat for nighttime application to drive the continuous cycle, the thermal TS system is implemented through the phase change material. Similarly, in figure B, you can see the phase change material is been filled in certain region of the house. So through the solar collector in the rooftop, the and the heat transfer fluid, the energy has been stored in the phase change material while the daytime. And when the cold winter night, the we want to heat the house, that time this energy can be again reused through the same pipelining through the heat transfer fluid and heat exchanger. We can make the house warm. So this is the certain application of the phase change material. Now, performance enhancement techniques for the thermal energy storage material. As we already discussed, certain limitation of the phase change material. Phase change material are facing some problem, that is the low thermal conductivity that can be correlate with the heat transfer. As the thermal conductivity is low, the heat transfer will become low. So to improve the heat transfer, definitely we need improved heat transfer. For any application, thermal application, the heat transfer should be high. To improve the heat transfer, we need to improve the thermal conductivity. So in strategy A, you can see in the left side figure, in strategy A, this is the mechanical strategy. In figure B, you can see that is the material strategy. Both are the strategies for enhancement of the heat transfer. But strategy A, what is the difference between A and B? In the major difference is inherent material property of the phase change material. Inherent property of the phase change material is not tailored in strategy A. That means we are not going to change any thermophysical property of phase change material in mechanical strategy. While in case of B, through certain nanomaterials like CNT, carbon nanotube, 2D nanomaterials, we are going to change the thermophysical property. That means thermal conductivity, say for example. So in mechanical strategy, you can understand like fins. We already know about the fins. So we are incorporating fins, metal foams. So these kind of strategies, if we are utilizing to enhance the heat transfer, we are not changing, we are not altering the thermophysical property of the phase change material. And in case of B, we are changing the thermophysical property of the phase change material. Now the question comes, how the nanomaterials improves the thermophysical property, or we can say thermal conductivity of the phase change material, that we are going to discuss in our next slide. See, in next slide you can see there are functional fillers. Now the terms comes functional fillers. A filler that performs certain functions in phase change materials. Fillers means what? Whatever things we are going to mix with the phase change material, that is defined as a functional filler. So functional fillers are a material that improves the thermophysical property. So left side you can see functional filler has been categorized in based on their geometry. Zero dimensional functional filler, one dimensional, two dimensional, or three dimensional functional filler. Whereas in the B side, right side, you can see figure B, the functional filler has been categorized based on their material properties or their material characteristics, like carbonic fillers that comes like CNT, CNF, graphene, graphene oxide, carbon foams, that are the carbonic fillers. Ceramic fillers like Al2O3, TiO2, SiC, ZNO, MgO, boron nitrate, that are the ceramic fillers. Similarly, metallic fillers like copper, uh, nickel, aluminum, and silver. This kind of nanoparticles comes under metallic fillers. Polymeric filler also like PVA, aerogel. These are the polymeric fillers. So both both are providing same functions, but they are categorized based on their dimension or based on their material properties. Now the question arises, how this 1D or 2D or 3D fillers can improve the thermal conductivity. So functional fillers and thermal performance. So thermal conductivity. I am taking example of CNT because it is a most widely employed functional filler for the phase change material. So thermal conductivity through CNT, increase significantly thermal conductivity in PCM, enabling faster heat transfer during phase change. This improves the efficiency of energy storage and release. Heat transfer also, the addition of CNT reduce thermal resistance within the PCM matrix, ensuring uniform temperature distribution over all the material, so that we are getting the uniform heat storage in the phase change material or thermal energy storage system. High latent heat retention. The one of the major disadvantage apart from the thermal conductivity is that when we are implementing any functional filler in the phase change material, it reduce the latent heat capacity. Latent heat capacity of phase change material reduce when we are mixing certain fillers. Why? Because the storage of heat taking place only in the phase change material, not in the functional filler. Why? Because phase change because thermal heat is storing in the material, not in the functional filler, because functional filler is not changing its phase, and what we are storing heat when the phase is changing of the material. Basically we are storing latent heat. So who will store the latent heat? The material who is changing the phase. Oh, right. So phase change material is okay, it is changing its phase and storing heat, but if we are incorporating the functional filler that is not able to change its phase at certain at the operating temperature, so it will not contribute to the latent heat, and it will occupy the volume of the material. Overall volume of the material will get reduced if we are mixing the functional filler. So definitely it will reduce the latent heat. But in case of CNT, definitely it will reduce the latent heat, but it will reduce significantly lesser as compared to the metallic nanoparticle. So because of this, we are using CNT as a most of the research. You can see CNT is a nano functional filler for high latent heat retention. Structural stability also. The network structure of CNT helps to maintain the integrity of the PCM, that reduce the leakage while the material will change phase and improve the long-term stability. Now, this next point is a photothermal conversion. That is the new point. Before we have not discussed this point. Like certain, if we are going to implement phase change material to direct convert solar energy in the form of light. uh, Solar energy, how we are getting solar energy in terms of light. So if we want to convert light directly to the heat, and directly we want to store that heat in the latent heat material or phase change material, so certain filler should be there that will convert light to the heat very rapidly. So in that case, CNT has been employed. It has been mixed into the phase change material that will convert light to the heat, and the phase change material will store that heat inside itself. Then supercooling, durability and reusability, and customized thermal property. Through this CNT implementation, we can reduce the supercooling, because CNT acts as a nucleation sites. When we mix the CNT in the phase change material, it creates more nucleation site, so that the supercooling effect is get reduced. Durability, because CNT is having such property that we can use uh, multiple cycles for phase change material, so it will reduce the it will improve the durability. And also customizable thermal property. By adjusting the concentration of functional filler of CNT, we can customize the thermophysical property of the phase change material. Okay, now I would like to say, through this picture, I would like to explain how the functional filler will improve the thermal conductivity. You can see zero, whatever the filler, 0D, 1D, 2D or 3D, these all kind of filler will reduce the phonon scattering, or in short we can say it will reduce the barrier to flow the heat, or we can say it will provides a path. You can see in the picture, when we are mixing functional filler, it will provide a path through that heat is transferring. So these are the strategies that will reduce the thermal resistance, and it improves the thermal conductivity of the phase change material. So phonon transport, actually, what is phonon transport? Basically, phonon transport is responsible for the heat transfer. So phonon scattering is induced by the mismatch interface between PCM and supporting material. Like carbon material, it creates a efficient thermal pathway, that is a 1D linear 1D material like CNT, it will creates a linear path. 2D material like graphene, it creates a planar path, two-dimensional path. Or 3D materials like carbon foam, it provides a network path that is a more effective. So through these 1D, 2D or 3D material, the we are finally what we aim to reduce the thermal resistance, so that we are getting high heat transfer. And also some chemical methods are there like surface functionalization and techniques of surface functionalization. Through that also we can improve the thermal conductivity. So basically these chemical methods are for the functional filler, not for the composite. First we have to functionalize the nanofiller, then after we are going to mix these kind of filler with the phase change material that will improve the thermal conductivity. So in these techniques, functionalization, two type of functionalization, surface and chemical. So chemical functionalization, what it it attach the functional group like hydroxyl and carboxyl groups in the nanomaterial, so that it will reduce the phonon scattering. Physical coating, doping, and plasma treatment are also such method that will improve the surface functionalization. And after that, we can mix this nanomaterial to the phase change material. So this is the surface functionalization and thermal conductivity, and this is a uh, conclusion of surface functionalization for thermal conductivity and surface functionalization for phonon scattering. Both are interconnected. So surface functionalization and thermal conductivity, what it does, when we do surface functionalization improvement, it improves the interfacial bonding, enhance phonon coupling, alignment of lattice structure. This is little more deeper for the material size background, so I'm not going to discuss this in more detail. So I wish to show you some my previous work, what we did in for the similar approach to improve the thermal conductivity or thermal physical property of the phase change material. So in our recent work, we have mixed the copper oxide functionalized CNT. Means we have decorated the copper oxide nanoparticle in the CNT surface of the CNT, so that we are getting improved result as compared to the pure CNT. Why? Because this additional attachment of copper oxide on the CNT surface, that creates more nuclearization side. When the material is changing its phase from solid to liquid, there is a crystallization process. So if we are mixing this nanofiller, this specific nanofiller like copper oxide coated CNT, it creates more nuclearization side, so that we are getting better response while the phase change. It will store more amount of heat as compared to the pure CNT. In this case, we have synthesized the CNT, then we mix with the phase change material through sonication. We prepare a uniform distributed composite, and we get solidified phase change material. What we have done after that, we have done some chemical characterization to um ensure the composite, whether any chemical reaction is taking place or not, through FTIR. and through Raman spectra also, no such new chemical composition has been observed. So we ensured that what we was targeted, that has been achieved without any new functional group has been generated. This is some SEM image of the material what we nanofiller what we have prepared. You can see in the picture that CNT has been decorated with the copper oxide particles. Later we have mixed this nanofiller in our phase change material, that is paraffin wax. Paraffin wax we have used as a phase change material. So this is the distribution. We have correlated the distribution. Also, I would like to um, introduce the importance of distribution of the functional filler in the phase change material while we are synthesis the composite. So we have analyzed how the distribution of this filler uh, influence the thermophysical property of the phase change material. We prepared four sample, and by changing the ratio, weight percent ratio of the functional filler in the PCM, and analyze the distribution. So we have done the thermal analysis, TGA, DSC, and thermal conductivity also, and got some significant results that shows that such kind of functional filler with mm, chemically treated, or we can say chemically functionalized CNT gives the higher thermal conductivity as compared to the pure CNTs. This is the result of photothermal conversion efficiency. What we did, I can show in the next slide. This picture can you can see in this picture we have used the solar simulator, that is an experimental setup. We create artificial solar radiation through the xenon bulb. The xenon bulb has been kept in the top of the our sample, that is the paraffin wax mixed with the copper oxide coated CNT, and we analyze how the temperature of the phase change material is changing. So this plot you can see, in the plot B you can see the pure paraffin wax is not even getting such temperature so that it will start melting, whereas the composite mixed with the copper oxide coated CNT is getting more significant temperature rise, and even the material is start melting also. So through that we can understand the functional filler importance of functional filler. If we are mixing functional filler, the melting temperature can be achieved directly through the solar light without any heat transfer fluid. So this kind of material can be utilized to store direct solar heat in terms of latent heat energy storage material. And also we have achieved the thermal efficiency, photothermal efficiency around 67.4%. So this is a significant achievement that we have done with the copper oxide coated CNT mixed with the paraffin wax. And also we have done some simulation work to understand the importance of functional filler for cooling of electronic devices. So we have created a geometry with fins. You can see in figure A that that geometry is nothing, it is a uh, CPU of computer. So in the top of the computer we have attached this the CPU. We have attached this fin kind of arrangement and filled with the PCM, and observed how the thermal management is taking place with or without PCM. The temperature drop of the CPU has been microprocessor has been analyzed with the PCM, because when the processing of computer taking place, it generates heat. That heat need to be taken away from the microprocessor. So we have employed the phase change material to take out the heat. So these are the some results. I think uh, this is another part. So I would like to show this part very briefly. Multifunctional PCM. So far, what I discuss is the thermal energy aspects. Now the terms multifunctional PCM. So I would like to say like uh, PCM cannot be only to store the heat. Nowadays, when the material efficiency is considered or effectiveness is considered, or conclusively we can say sustainability. So in that case, if we are synthesizing a material, so material should be perform multiple tasks, not only the thermal energy storage. In case of PCM, I would like to say the PCM should not perform only one application, that is the heat storage. Instead of that, if we are getting different applications, like I will show in next slide also. Like this is the milestone of phase change material for multiple application. It starts from 1990 through CNT, and it it has been finished in, means it is progressively increasing, but till 23 the nanomaterial like tetrapod has been utilized. Tetrapod is a specific design created by the chemical reaction of the carbon material. So from fundamental, from CNT, the development has been taking place through different material, CNT, graphene oxide, and different materials like magazine also. Till 23 different like tailored material has been designed, and it has been mixed with the paraffin wax, or in general we can say fashion material, to get the desired thermal conductivity or designed thermophysical property. So now for multifunctional application, as we discuss only the energy storage, but PCM can perform different application like for cooling and heating of buildings, cooling and heating of the uh, wearables like jackets, or we can say the uh, life science also. Thermoelectric generation, through thermoelectric generation means if we can create temperature difference, certain thermoelectric modules can utilize that temperature difference and create the electricity. Similarly, electromagnetic shielding also, if we synthesize a phase change material with certain nanofillers, that will restrict the electromagnetic waves. So this is another application of phase change material, like photothermal conversion, greenhouse effects. We can use the phase change material in between the walls of the greenhouse, so that it will maintain the temperature. So through this image you can see phase change material is not only for storing the heat, that can be used for the different applications also. These are some chemical we will not going to discuss this thing. Like you can see the application of phase change material. Here you can understand the thermoelectric conversion. What is the thermoelectric? So in figure A you can see a thermoelectric module which deals with the temperature difference. In the top side, the hot top side of the thermoelectric module, the temperatures would be higher as compared to the bottom side. So what we can do in this case, we will put the we can integrate the phase change material on the top side, and we will keep this entire module in the solar light, so that what will happen, solar light will incident on the phase change material and it will increase the temperature of the top side. So automatically the temperature difference will create, and this difference temperature difference can be utilized to generate the thermoelectric energy. So this is certain application of thermoelectric conversion through the phase change material. Even the thermoelectric module can implemented through different temperature difference, but PCM can be help to generate certain temperature difference even when there is no availability of the heat source. Why? Because PCM stores heat in the daytime, and it will retain the heat till the temperature till the source is disappear. After that also this heat can be utilized in the thermoelectric module. So this is a photothermal conversion setup. You can see in this picture, when the light incident, the temperature of the material is getting rise, and further this will connect to the thermoelectric module. then again the temperature difference will create and it will uh, utilize to generate the electricity. So these are some examples and some research work for photothermal conversion. So another application is a building application of the phase change material. So in building application, what generally the research is going on is that phase change material is filled among the walls, windows, floors, and even in the bricks. The bricks is not a usual brick. That bricks is some hollow space, so that phase change material is filled in the bricks. The it will restricts the heat to penetrate the wall, and it will keep the house cold in the summer case, because when the heat will try to enter the wall, the PCM filled among the walls, among the bricks, it will start melting, and the heat will not further go towards the inside room. So this is some example of phase change material in buildings. This is certain example how the temperature drops at what temperature, like some simulation has been performed, and it has been observed that through the application of phase change materials, around 12 to 12 to 20 degree temperature drop has been observed in the case of hot summer. So this is another experimental setup. We can see how the phase change material has been integrated to the wall, uh, so that the temperature rise in the wall inside the house can be reduced. This is the latest research what is going on nowadays with the PCM. Nowadays PCM has been developed for the flexibility, so that flexible PCM can be attached to the for the medical therapy, thermal therapy, uh, for getting thermal effect in the body. If we have pain at certain region that need to be conquered through the heating, so in that case thermal patches are developed. That patches is made with the phase change material, and if we are wearing that phase change material, embedded patches in our body, and we if we are moving in the solar light, that patches will automatically get warm and it will provide the thermal therapy for the affected area. So this is the latest research going in the case of flexible phase change material. So this is the consideration for phase change material based on the variables for flexible phase change material. Certain consideration is there, that should be store high energy material compatibility. The material should be chemically stable over a long period to prevent degradation, and it should be compatible with the textile, or should be uh, it should not cause any structural damage to our uh, textile or our cloths. Encapsulation and leakage, the material should be easy to encapsulate, so that that kind of thermal patches can be designed. Encapsulation should be maintained in thermal property while ensuring even encapsulation can be done, but flexibility should be also there. Otherwise, if you will wear, the material will not flexible, the patches will become broken. So even and also thermal conductivity, definitely thermal conductivity should be high, so that additives like carbon nanotube, metallic nanoparticle has been integrated to improve the thermal conductivity. And also the weight of the fashion material should be very low, so that uh, it should be lightweight and breathable to avoid the discomfort of the uh, wearing person or integrated into the fabrics. Similarly, mechanical durability, biocompatibility, like biocompatible materials should be used so that it should be non-toxic for safe and long-term skin contact. Someone is going to wear this kind of fashion materials, so that it should be safe for skin contact. And definitely manufacturing cost should be low. Environment and regulatory compliances should be followed by the phase change material. This is another application of phase change material. Uh, I think I would like to conclude with this application. This is the desalination of water. So to convert the sea water or harsh water to the potable water, phase change material takes place. Can show the its importance, because when desalination, without electricity, if we want to convert salt water into the drinking water, daytime it is possible through solar light. But what about when the day solar light is not available? In that time we can store the heat in the phase change material, and after the set of the solar energy, the same stored energy can be further utilized to desalination process, so that continuous outcome of the desalination technology can be achieved through the phase change material. So at last I can conclude that phase change material have long been recognized for their role of thermal energy storage that offers latent heat capacity and enabling efficient thermal regulation across various applications. However, conventional PCM face significant challenges, like we already discussed, like thermal conductivity, phase segregation, and supercooling, that can lower the practical employment of phase change material in advanced energy system. So the integration of nanotechnology through nanomaterials can transform this approach and overcome these challenges. So key advancement of phase change material is enhancement of thermal conductivity, optimize the structural stability, like nanostructure filler. If we will implement these kind of fillers, it will reduce the phase segregation, leakage issue, and improve the durability over the repeated cycles. And such kind of fillers, whatever, whether it is 1D, 2D, or 3D fillers, that will improve the photothermal conversion also. So that will improve the implementation of phase change material for direct solar to heat storage. Supercooling and suppression, certain nanofillers will increase the nucleation side through nanomaterials that will minimize the supercooling effect, and it will ensure the phase transition and enhance thermal conductivity or thermal regulation efficiency of the phase change material composite. Even for multifunctionality also, the integration of nanotechnology allows the PCM to exhibit additional functionality apart from the thermal conductivity or thermal aspect. It will improve other aspect also, like electromagnetic shielding, optothermal or photothermal conversion. It provides the mechanical strength for the phase change material when particularly we are dealing with the flexible phase change material. So this kind of nanofillers improves the multifunctionality of the phase change material composites. So in case of future research, we can consider the advancement of nanotechnology that redefines the capabilities of PCM, making them more versatile and efficient for modern thermal energy storage application. That moving forward in the research of PCM composite, we should focus on the optimized filler dispersion techniques, that we already seen that dispersion of the nanofiller in the PCM composite is we play a significant role for thermophysical properties. So that for future research we can consider the dispersion techniques also, surface functionalization strategies, hybrid nanocomposite to improve the PCM performance. Additionally, sustainability should be considered as a top priority, emphasizing the development of eco-friendly nanomaterials, because whatever the materials, most of the research is taking place, that is a that are not an eco-friendly material, that are the maybe chemical treated material or chemically materials. So we should consider the eco-friendly nanomaterials, and that should be scalable for manufacturing process also. Such materials to develop at a R&D scale is okay, but the material should be scalable for manufacturing process also. As the demand of efficient energy storage and thermal management solution continues to grow, nano enhanced PCM are poised to play a critical role in shaping the future of sustainable energy technologies. By utilizing the synergy between nanotechnologies and phase change materials, researchers and industries leaders can unlock new possibility for thermal performance energy system, driving innovation in renewable energy, smart buildings, and next generation electronics. So these are the some future research that we can consider for phase change material based thermal energy storage applications. So with this small information, I would once again like to thank the organizing committee and conveners Dr. Siva Kumar and Dr. M. Vinod for inviting me for discussion on the topic. So thank you, sir. So if you have any question, please you can ask.
So, chat box, we can put, I consolidated the questions asked by participants.
Okay, okay, okay.
So, first
I can.
question is, what are the key material design criteria for developing multifunctional PCMs behind just heat storage, storage capacity, latent heat storage capacity?
Sir, what is the question? Can you ask again?
Sir?
What is the question, sir? It's little hard to listen.
Yes, sir. What are the key material design criteria for
Okay.
developing multifunctional
Mhm.
PCMs
Okay, okay,
behind
okay.
just latent heat storage capacity?
Okay, okay, understand. So to develop a multifunctional phase change material, the key criteria is the integration of nanomaterial. Like, uh, can you please mute the mic, sir?
Sir,
Can you please can you please mute the mic? There's some disturbances.
1 minute, sir. 1 minute. Sir.
Okay, I think now it's okay. So to designing multifunctional phase change material apart from the thermal energy storage, actually to get multifunctionality, we need to incorporate not only single nanofiller, we have to incorporate different nanofillers. So the chemical compatibility and the techniques through which we are synthesizing the nanomaterial is the most important criteria to design the multifunctional material. And also the thermophysical property and concentration of the nanofiller also takes place very important role for multifunctional material. Like if we are integrating the nanofiller for EMI shielding, in case of EMI shielding, we have to integrate the material like cobalt, nickel, even magazine also can perform this thing. But after certain concentration, other properties like latent heat is getting significantly decreased. So I can say the concentration of the nanofiller is the most important criteria that can play a role to design a multifunctional material.
So, another question is, how can machine learning or computational material design accurate the discovery of high performance PCMs?
Okay, actually, this is not a my research area, but I will try to answer this because I never tried the machine learning.
Sir, I think we lost your network, sir. Hello. So I think We lost your network, sir. Dr. Manmohan, sir.
Vinod sir, please wait. Actually, he's coming back. His system got switched off, so he's coming back.
Okay, sir. We will wait, sir.
Hello. Hello. Mr. Vinod. Hello.
Sir,
Sorry for disturbance.
no issues, sir.
So
So I
I,
think the next question is how can machine learning or computational material design accurate the discovery of high performance PCMs?
okay. Uh, as I was telling that this is not my research area, but what I have studied in few research article like machine learning has been employed for prediction of some thermophysical properties. In that case, thermophysical property is based on the material. So we have to categorize the material, and for that particular category, we have to collect the data set. So that through that data set, like around 200, 300 data set, if we have, then we can implement the machine learning to predict the thermophysical property. It will reduce certain experimentation process. So, like if you want to predict the thermal conductivity, other properties like latent heat or specific heat, in that case, that machine learning, if we will train the machine learning, if we will put the concentration, definitely we can get some predicted value of thermophysical property. So as per my knowledge, machine learning will definitely help. It will reduce the experimental work, but in that case we have to be concise. We have to collect very concise data set, not in the broad way. Like if we are considering phase change material as a paraffin wax and considering CNT one dimensional material, so our data set should be in that category only. If we will consider other nanoparticle also like copper oxide, magazine, and graphene also, that in that case the data set will not give the accurate prediction. So I think up to this only I understood what how the machine learning can be predict the thermophysical property of the phase change material.
What are the current advantages in PCM application for thermal management in electrical vehicles and aerospace?
Okay, so the most widely research area for electric vehicle is the battery cooling. So as you know, I think everyone knows that the major issue of battery is the overheating and the damage of the vehicle because of overheating. So in that case, the phase change material has been employed to uh, reduce the temperature of battery. So phase change material can be filled around the battery bank, so that when the temperature will get increased, the same amount, the similar heat can be extracted by the phase change material, and it will reduce the temperature of the BTS, battery thermal system. So this is the major research work going on the battery vehicles.
I hope audience will get their answer for the posted question, sir. Hello,
Yes.
sir. Dear participants, do you have any questions to ask? Dear participant, you can unmute your mic and you may ask or post your questions in chat box. So we want to move on for next session. So if you have any question, you can directly unmute yourself and ask the question with our expert, or else you can post. I think so. So we are concluding the session with a thanking notes to our Dr. Manmohan sir. On behalf of the organizers and participants, I take this opportunity to sincerely thank our esteemed resource person, Dr. Manmohan sir, for delivering such an insightful and engaging session today. Surely your expertise and valuable inputs and practical perspective have enriched our understanding and made this session really truthful, sir. So once again, we are grateful for your time and effort. You are dedicated to be with us for sharing your knowledge. Uh, Once again, I am thanking you, sir.
Thank you, sir. Thank you so much for having me on this FDP. With the hope we will meet again. So thank you.
So already our next session guest is also joined with us.